Hello, I'm Anne Bennett from the University of Colorado Boulder, and today I'm here to tell you about identifying minor debris strikes in spacecraft telemetry, specifically the methods that I've been developing and the applications that we've done so far with those methods. So to begin with, let's set the stage with discussion of hazardous non-trackable orbital debris. Essentially, anytime you have an event on orbit where it's a satellite fragments, you'll read a space news article and it might be like, oh, 7 events were created, or 7 pieces of debris were created, or 40 pieces of debris were created, or in a really bad one, it might be more. But the thing that they sometimes don't mention is that these fragmentation events will actually produce clouds of small debris as well as the larger trackable pieces. To set that context, the space surveillance network tracks down to about 10 centimeters in LEO, but only down to about 70 centimeters in GEO, which is actually less than 10% of the debris that could potentially pose a hazard to spacecraft. For example, over here we have a NASA test of a 1 centimeter sphere impacting a battery through a structure wall, and it did some pretty severe damage to said battery. However, sample return missions indicate that satellites come down with hundreds to sometimes even thousands of impacts. For example, the Long Duration Exposure Facility, Hubble Solar Arrays. So we know that spacecraft on orbit are getting hit by stuff, and most of the time it doesn't make a difference. There's an example of recent events. We've got Sentinel-1A, World 2, the MMS constellation. A lot of these spacecraft have kept on operating. However, we have other spacecraft which have experienced abrupt anomalies. It's hard to tell for sure if it's debris or not. But debris is definitely a plausible cause of those mission losses. So the main punchline here is just that these untrackable strikes can be benign or they can be catastrophic. So how do we deal with this problem? Essentially, we do it with modeling. ORDIN is the NASA tool that US programs generally use to predict the expected debris flux in their spacecraft orbits. However, it is fundamentally limited by data collection systems, and it only models debris down to about 10 centimeters in GEO, and that's extrapolated from the 30 centimeter data. We haven't actually collected data on debris that is less than 30 centimeters. On the other hand, in LEO, a 2017 NASC report evaluated predicted versus reported anomalies and found that there were significant inconsistencies where there were actually far fewer anomalies reported than predicted in multiple case studies. For example, one study predicted between 24 and 160 perturbations, and they experienced 7. So the recommendation of that NASC report was to collect additional data to validate those models. And for typical spacecraft operations, historically, this is definitely changing as we have these larger constellations coming online. If there's anomalous behavior, you get this full review, which is significant time and money. But if there's no anomalous behavior, sometimes things might possibly be missed. The indications of debris strike are often very subtle. So the question is, can we look for these subtle strike effects that don't necessarily do any damage to the spacecraft, but might, if we detected them, give us some insight into what these non-trackable debris populations look like? So started out by modeling the spacecraft dynamics. Essentially, with the research goal of developing these techniques, the place to start is what happens when a piece of debris hits the spacecraft. And for most debris strikes, it's going to impart a rotation to the satellite, assuming it's not square on the CG. And that will be corrected by the attitude control system for most satellites. But there's still an abrupt change in the angular momentum of the satellite. So this is kind of the rate abrupt increase in correction. But over here, you see the abrupt change, which I refer to as a delta H. To kind of prove out this model, this is the Sentinel-1A debris strike, which saw the exact same sort of a feature. So the desired outcomes from this research are that if we learned how to monitor just kind of typical satellite telemetry for subtle perturbations that might be indicative of impacts, we could start using most active spacecraft as in-situ debris sensors. That would allow us to acquire data to validate these models and, of course, monitoring spacecraft state of health. So I tried 2 different ways of doing this. They both worked okay, but the change detection ended up being kind of the clear winner, at least for the type of telemetry that I was analyzing. The first way that I just tried was using a digital signal processing technique called a match filter, which I applied to that wavelet that we saw in the rate telemetry. And essentially, this is the kind of the concept is that this is the signal that we're trying to find for digital signal processing, and it's what the spacecraft telemetry will look like when a strike occurs. So you can see that if we have this wavelet, which we slide down this data, you have this strike here at t equals 50 seconds, where the telemetry kind of wanders up a little bit and then wanders down a little bit. But just eyeballs on telemetry, you're not really going to notice that because it's pretty well hidden within the noise floor of the data. But if you do this digital signal processing, where on the matched filter on the data, you actually manage to show this really clear spike at the time of the strike. So that does a fairly good job. But what works even better is these change detection algorithms when we apply them to the angular momentum telemetry, because the inertial angular momentum nominally should be quiescent in the absence of an external torque, and a debris strike will impart an abrupt external torque to the satellite. So you should see this abrupt change in the data. And even for a very subtle change that's very hard to pick out, just looking at the telemetry, you get a pretty distinct spike above the noise floor. So that was worked pretty well. One other important note is that setting these detection thresholds for deciding within your algorithms, like what level do we decide as a strike and what level we don't decide as a strike, is a bit of an art form, and it depends on your objective with your project, whatever you're doing. So if you set your thresholds low, you're going to trip the detectors on a lot of features that you're not quite sure they may or may not be debris strikes. If you set it high, it will only catch the more distinct features, so you might miss debris strikes that you could have detected, but it will, when you do detect a debris strike, you'll have a lot more confidence in it. So essentially, these graphs are just showing the kind of the statistics of the matter, where any strike that's delivered to the spacecraft will have kind of a, it might have produced a large effect, it might produce a small effect, just compared to where the telemetry is at that time. So the idea is that depending on where you set the threshold, you're going to have a certain probability of false alarm where there's no strike, but you thought there was one, or you have a certain probability of a misdetection where there was a strike, but the blip was too small and you didn't catch it. So depending on where you put this threshold, you can kind of trade those two values and essentially just decide whatever false alarm rate you can tolerate and go with that. So with those algorithms, I had the opportunity to start applying them to some real telemetry. This is very much a work in, well, sort of a work in progress. At some point, hopefully we'll get access reestablished. But essentially, when you apply it to real telemetry, things get kind of complicated and murky, and it's difficult to tell what's real and what's not. So essentially, this was NASA's Solar Dynamics Observatory, which has this strange square wave in the angular momentum, which should theoretically be quiescent, but spacecraft are strange. And so we had to do this pre-filtering to remove that, which just sort of introduces some uncertainty to the results that come out of the filter. What I found was I found a lot of small blips. Naturally, I had my threshold set pretty low in order to detect these smaller things to see what we could find. So given that I have this low detection threshold, I would expect to see routine false alarms. But the question is, how would we tell if these are false alarms or if they're real? So for starters, I looked at these two biggest events to see what could be seen in the telemetry there. And these were pretty confidence building because given this momentum telemetry, you would expect the debris strike would cause an abrupt change in perturbation, change in the angular momentum, and we see that here. So the filters are doing the job that we expect them to do, and they are identifying these abrupt perturbations and pulling that out of the data and giving us a very strong response. So that's good. What's not so good is that for this particular debris strike, the reaction wheel telemetry gets odd like an hour before the strike. So it's probably that's throwing the angular momentum off, and I'm not sure what's going on with this reaction wheel, but it's probably not actually a debris strike. Similarly on this one, first I kind of felt like this was probably a debris strike, and then I talked to the ops team and they're like, no, actually we switched the inertial reference unit's heaters on at shortly before this, so they probably just warmed up and like changed the measurement. So good news, they're identifying the perturbations that we want them to. Not so good news is they're not actually debris strikes. So That's what we had on SDO. So those were the larger blips. The other question was, what about all these small blips? So remembering how I set the thresholds, I set them pretty low. So we would expect routine false alarms. And if they're at kind of a consistent level where you're getting like a couple per day, then you would kind of expect that that's what you would expect to see. The things that were surprising is that they weren't consistent. There are some times of the year where you experienced substantially more blips than other times of the year. So it's like, that's kind of odd. I wonder what's going on with that. And basically, at first, I kind of assumed they were just noise. There just seemed to be way too many of them, and maybe they still are. We're not quite sure yet. But anyway, the surprising thing about all these patterns that we see here is that they kind of, sort of, not really, but maybe line up with these measurements of the sporadic annual variations in micrometeoroid flux, which we got really excited about. But then I had NASA, down at NASA Mars Patrol, they ran the models for me, and they were like, yeah, not a chance, because we would expect a few per year, not this many strikes. So nobody's really convinced that these are anything real. But one thing to note about them is we can't really do tests in the micrometeoroid velocity regime. We can do tests in the low hypervelocity, not at the 10 to 60 kilometers per second. We can do tests of very, very small particles, but we can't actually test a hypervelocity or a micrometeoroid impact. We can't shoot them fast enough if it's a large enough particle. So we have no idea what this momentum enhancement factor is here. So that might be throwing the models off, but it's still very much an open question. Anyway, the other satellites that I looked at a little bit were these magnetospheric multi-scale missions, which is 4 spacecraft flying in an elliptical orbit, highly elliptical orbit. They are spin stabilized, have these really long wire booms, which adds a complication because every time they fire their thrusters, those wire booms start oscillating, and it takes like 10 days before oscillations decay to the point where I can start running my algorithms again without having a lot of false alarms. So found some interesting things. For one, we already knew about this debris strike, or possibly micrometeoroid strike, but the filters did manage to detect the one that we already knew about, so that was kind of cool. And then the other weird thing is that the spacecraft appeared to be torqued whenever it went through perigee. And I'm like, okay, so I don't know, gravity gradient, maybe let's go ahead and blink the results whenever the spacecraft is near perigee. But that torque isn't applied consistently relative to the spacecraft's position relative to Earth. Sometimes it's a little bit, before the spacecraft gets to Earth, sometimes it's a little bit after, it just kind of slides around. And then I saw something even more odd, where there are also times where I get these, what I've started calling mystery torques, because the spacecraft will be out at apogee, which is like 70,000 kilometers, and all of a sudden something's torquing the spacecraft. Like, what the heck could that possibly be? So the theory is, MMS flies through this region to study magnetic reconnection, and it's a very electromagnetically kind of active region, which of course is changing in response to solar storms and all that kind of stuff. So my completely unvalidated theory is that this very long charged spacecraft is flying through these electromagnetically active regions, and that interaction is kind of applying a slight torque to the spacecraft, which is scientifically interesting, but not a debris strike. So that's where we're at with that. The last thing that I wanted to talk about is actually just potential applications for these methods, because well, these 2 spacecraft, I haven't quite gotten the results ironed out enough to where I'm really confident in them due to the COVID pause, but yeah, maybe hopefully at some point we'll get there. And so if we did manage to get these techniques returning useful data, like what would we do with that is the question. So the first and obvious thing, if you're just a single operator, the benefit that you get from flying these would be state of health monitoring, and of course anomaly attribution and anomaly response, where it would be pretty obvious right away that something was torquing your spacecraft unexpectedly. So that's interesting. Also, if you had a debris strike that caused damage to your spacecraft but didn't cause an immediate anomaly, that might kind of give you a leg up on figuring out later on when your Star Tracker has stray light issues, what might have been the source of that issue. However, another thing, especially if you were like a constellation operator and flying a lot of satellites in kind of the same constellation to collect a lot of data, you could improve kind of your knowledge of your own local debris environment. And also, A lot of people talk about, oh, we should use satellites as sensors kind of generically, and like, okay, great, here's one way to do it. So that's what we've got there. But kind of broadening the optic a little bit, like what else could this data be used for? With space traffic management responsibilities transitioning to the Department of Commerce, there's been some interest in an open architecture data repository for SSA info. And one thing that this paper by the Institute for Defense Analysis, Joel Williamson, suggested was if we also include a database of orbit perturbations, we could kind of collect data from a bunch of satellites and feed that back to our models and hopefully help to tune our models and our model parameters and our understanding of the small debris population. So model validation would be a good way to do that. And it also allows us to collect data in regimes that are currently pretty poorly modeled. For example, GEO, we just don't have a heck of a lot of data on what the small debris population looks like up there. And this is one way that we could potentially start measuring it a little bit. So conclusions are that hazardous non-trackable debris is an ongoing challenge to safe space operations. And the reason for that is the models are very good based on the measurements that we have. We just don't have a heck of a lot of measurements. The data that we can collect on these small debris populations are very limited, and discrepancies or uncertainties in the models are probably due to that, and also just uncertain parameters and how to turn the data that we can get into how does our spacecraft actually get damaged. So that's one takeaway. Change detection algorithms are like pretty darn good at highlighting unexpected perturbations in telemetry, but they also, when you actually run them on, when you run them on simulated data, everything is beautiful. When you run them on real world data, things get weird. And the disappointing thing about that is it makes it harder to detect debris strikes. But the nice thing about that is it could have utility for monitoring just the general state of health of the satellite. Then of course, besides that state of health on kind of the local single operator level, if we could contribute this sort of data to a central database, perhaps we could learn some more about the small debris population. With that, I'll turn off the recording.